So in this lecture, we are going to talk about measurement of the dielectric response of a dielectric material. Now, when you have a dielectric, the essential feature of the dielectric is that it is polarizable. It undergoes polarization. And therefore, in this dielectric response measurement, what we attempt to do is we attempt to measure the polarization and the depolarization process. When I apply and when I energize a dielectric, polarization will happen, and when I remove the energization, when I remove the supply from the field from the dielectric will depolarize. And the manner in which the material polarizes or depolarizes can be a good pointer to the quality of the insulating material. So we are going to here apply the polarization and depolarization measurements for assessing the quality of the insulating materials. The procedure is rather simple. You just need to measure two currents in some way or the other. The challenge lies in the analysis of the data. How do you relate the variation in the polarization and depolarization data to changes in the property or in changes in the condition of the material? However, dielectric response measurements can yield valuable information, for example, regarding the moisture content in the insulation, because moisture can be a problem in insulation. It can cause degradation of the material. It adds to a lot of additional losses. So dielectric response measurements can give us idea about the moisture content, of any possible contamination if you have a lot of impurities. So basically about the composition of the insulation, and most importantly about aging. When we are looking at we are trying to monitor the health of an insulation, the material degrades, and the polarization and the depolarization mechanisms change as degradation due to aging occurs within the material, and therefore these can be used as aging markers, and we are going to discuss how that happens. Before we do that, let us look at the polarization mechanisms briefly. We have indeed talked about polarization mechanisms when we talked about dielectric properties. Let us again look at what I mean by how does a material behave when it is polarized. Now let us look at the step response of a dielectric material. So I apply a step voltage, a DC voltage across the material. When I do that, I would have a current that is flowing through the material. This instantaneous current can be written as JT. And this current that immediately flows in the material, as soon as I apply the electric field across the material, will comprise of two separate components. The first is sigma naught ET, which, as you can see, is the ohmic component. So you apply an electric field E, and depending upon the conductivity of the material, a current component will flow. This is the DC ohmic current that flows in the material because of the application of DC voltage. This would flow even in conductors. However, in addition to, and almost of the same orders of magnitude, there is a second current which is due to the displacement current, which is del D del T. So when D is the flux density, the rate of change, the time variation of the flux density gives rise to a second current, which is the del D del T. So the total current is the sum of this conduction current and this displacement current. Now, this displacement current in reality comprises again of two components. What are these? Epsilon naught del E del T. If you remember, D is equal to epsilon E plus P. So the flux density comprises of epsilon naught E, which would be the flux density if there was no polarization, where epsilon naught is the permittivity of free space. So epsilon naught E is the flux density when you have free space and you apply an electric field E. In addition to that, because of the dielectric material, because it either has dipoles or can cause dipoles, and these dipoles orient themselves in the direction of the field, there will be a second current, and this is del P del T, which is due to the time rate of change of polarization. Now, if you have vacuum, you will have the second component, but you will not have the third component. In a dielectric material, which is non-vacuum, you will have both these components. So therefore, the total current that flows in a dielectric as soon as you apply an electric field across it comprises of three currents. The first is the conduction current, the ohmic current, which flows due to a DC conductivity. Then you have what is called the vacuum current. This vacuum current would flow even if you had a vacuum material, and this is caused by the rate of change of the electric field. So if the electric field is changing, it's time varying, you will have a current which is given by epsilon naught del E del T. But in addition to that, you will have a component del P del T when you have a solid, or if you have a dielectric material which is not vacuum, which is a material, and this need not necessarily be due to the rate of change of the electric field, but has to be due to the change of the rate of polarization. If you have a DC electric field, E does not change. However, P can still change. So there will be a time rate of change of polarization even when you apply a constant electric field E across the material. And this is called the polarization displacement current. So you have the conduction current, then you have the vacuum current, and then you have the polarization displacement current. All these three things taken together gives you the current. And as you can see, I have drawn here what the polarization will look like. The polarization initially, when you apply an electric field E, this is the electric field that has been applied. As soon as the electric field is applied at time t equal to 0, we achieve an instantaneous polarization. This instantaneous polarization is the polarization at time t equal to t naught when the electric field E naught is applied at time t equal to t naught. And this is called the instantaneous polarization P infinity. Now, after that, as time passes, more and more polarization processes continue. Remember, there are many kinds of polarization processes that take place in a material. Some of them are fast processes, some of them are slow processes, depending upon the kind of polarization process. Some polarization processes may take a very long time to complete, whereas some polarization processes will happen instantaneously. So therefore, this P infinity must be those polarization processes that are achieved, that are complete almost instantaneously with the application of field. And then there are other processes which can continue over a very long time, and ultimately the polarization will reach a steady state. So as all polarizations are finite in magnitude, they will at long times definitely settle, and the polarization will finally become static. So the polarization at time t tending to infinity is called the static polarization. Now, depending upon what kind of material we are talking about, this time will vary. This time to static polarization will vary. However, what we understand is P infinity is the polarization that we will achieve immediately, instantaneously, and PS is the maximum polarization that can be achieved once you provide sufficient time. After it reaches PS, no matter how long you keep the voltage on, no more polarization is going to happen. And you will rise, the polarization processes rise exponentially from P infinity to PS. We also remember that Pt by E naught being the electric field applied, is given by epsilon naught xi t 1t. 1t is the unit step which is applied, and the response to that is given by Pt by E naught, which is governed by epsilon naught, the permittivity of free space, and xi t, which is susceptibility. So the electric susceptibility of the medium is a time varying quantity, and because of that, even when you have a step energization, you have a polarization which is time varying, and ultimately this time varying polarization will reach a steady state. And in between between this time t naught and time equal to infinity, there will be these currents flowing. Now, as more and more polarization processes get complete, this current reduces. The current due to del P del T, as polarization is achieved, there is the rate of change of polarization that is being achieved slows down, and this current slows down. However, this current is not dependent on the polarization processes and will continue to be the same throughout. So it's continuously, you will have the same value, and it will depend only on the conductivity of the material, provided that the temperature and conditions remain the same, then sigma E should remain the same. So as we have discussed, there are certain fast processes or instantaneous polarization processes, and then there are certain slow processes. Before we go on to discuss the slow processes, let us recapitulate what we have already discussed about the first fast processes. Now, the first polarization process that happens in a material is due to the separation, the electronic polarization, where you have the positively charged nucleus, and then around it you have the negatively charged electronic clouds. Now, in the absence of an electric field, the charge center of this electronic cloud and the charge center of the positively charged nucleus will coincide, and the atom behaves as a neutral particle. However, when you apply an electric field, there is an effective distance of separation between the positive and the negative charge centers, and as a result, a dipole is created. Now, in this creation of and then once these dipoles are created, they will align themselves in the direction of the field. Now, the creation of these dipoles and alignment in the direction of the field involves the movement of the electrons. Electrons are very light particles. They have very high velocity. So this process can be completed almost as soon as electric field is applied. So this contributes to instantaneous polarization. Similarly, when we talk about molecular polarization, where you have anions and cations, and these anions and cations normally their charge centers coincide, but when you apply an electric field, there is an effective distance of separation because of the movement of the cations and the anions in the direction of the field. Again, here, unless we are talking of very large polymeric molecules, these do not take a very long time. The particles are light and can move very fast, and therefore this process is also contributing to instantaneous polarization. So when we talk about P infinity, we are talking about these atomic and electronic polarization processes that happen almost in any material. However, depending upon the material of the dielectric, there are various other processes that will come into the picture. We have already discussed one of these processes, which is kind of not a very slow process, but depends on the depends on the material in question, and that is dipolar polarization or orientational polarization. In dipolar polarization, this happens generally in a polar material, where in a polar material you already have dipoles. You have dipoles already existing in a polar material because of their bond angle and bond angles and bonds lengths. There is a extra dipole separation. There is an extra separation distance between the charge centers, and therefore you have a dipole. When you apply an electric field, these dipoles will orient themselves in the direction of the field. Now, depending upon the size of the molecules which need to orient themselves, they can take small times or they can take long times. So depending on the material, the dipolar polarization will definitely take much more time than either. It's not going to be instantaneous, but it will take short times or long times depending upon the material in question. So now we will come to, having talked about these common processes which we have already discussed earlier. Now let us talk about some processes which are definitely slow compared to all these processes that we have discussed, including the dipolar process. And the first of this is the interfacial polarization. The interfacial polarization is predominantly effective in insulating materials which are composite in nature. So where you have either two different materials, two layers of materials, or fillers within another material, or even within the same material you might have two phases which behave differently, and there are interfaces. So interfaces between materials or interfaces between phases, no matter what. Now what you have is you have a mismatch between the permittivity of the two different materials, and you also have a mismatch in the conductivity. So depending upon the mismatch of permittivity, the stress distribution, so let's consider two layers of material. Let's not bother about two different phases or filler particles. Let's say we have two layers and there is an interface between the two layers. Now what happens is, because you have a mismatch in permittivity across the interface, the stress across the interface will be different. One of the materials, the lower material with lower permittivity, will be very highly stressed, and therefore that may have a higher voltage fall across the material, even if these materials are of the same thickness. The lower permittivity material will see high stresses, the higher permittivity material will see lower stresses, and accordingly there will be the voltage division. On top of that, so you see E, and then the current that flows through the material depends upon the conductivity as well as the electric field. So if you have J is equal to sigma E, if sigma E, if the sigma is different, and even if you had the same electric field on both sides of the interface, the current J1 will not be equal to J2, which means the number of charges flowing per unit time to the interface will not be equal to the number of charges which are flowing out of the interface per unit time. So basically there will be a mismatch between J1 coming in and J2 going out, which means your current law, Kirchhoff's current law, will no longer hold. You will not have divergence J equal to 0. You will have divergence J is equal to minus del rho del D, which means that there will be a divergence of the current density at a point on the interface, and that will be proportional to the rate of change of charged accumulation. So basically, because of the mismatch of permittivity, not only will sigma be different across the interface, but electric field will also be different across the material. So because of the mismatch of the product of permittivity and resistivity for the different dielectric clauses under the influence of an electric field, what will happen is at the interface, movable positive and negative charges will become deposited. So you will either have a net charge accumulation either of positive charges or negative charges at the interface of the material. So what I'm trying to say is this. J is equal to sigma E. Now across a material, the J that is coming in may be more than the J that is flowing out. As a result, there will be charge deposition at the interface. Horrible picture. Now, this phenomenon is very slow because you actually need charge to flow from one electrode to another. So this is free charge that we are talking about, and this is very important. So far, the kind of charge movement that we have been talking about are the bound charges. Right now, we are talking about movement of free charges. Movement of free charges under the influence of the electric field from one electrode to an interface where it sticks. And because of accumulation of charge, there will be a kind of charge separation between the charge on the electrode and the charge at the interface. So you really have a large dipole where you have equal and opposite charges, free charges and not bound charges, separated by a large distance. And because this involves the actual travel of charges, this phenomenon is very slow, and it is in general active in the power frequency range and below. Next, we come to trapping and hopping of charge carriers. What do we mean by trapping of charge carriers? We have discussed this before. When you have a conduction band and a valence band, let's say this is the valence band and this is the conduction band, you generally require enough energy for an electron to come to cross this energy gap and emerge into the conduction band. However, what might happen is very close to the conduction band, depending upon the material, very close to the conduction band, there might be energy levels which are vacant. So there might be positions in the lattice which requires an energy which is less than the conduction band but very close to the conduction band, pretty far away from the valence band, and these are called trap levels. When they're very close to the conduction band, they're called shallow traps. When they are closer to the valence band, they're called deeper traps. When I say shallow or deep, it is not about the height in the physical sense, but it is about the distance of the energy or difference in energy between the energy level here and the energy level in the conduction band. Now, if you have some charges which have energy very close to this energy level and there is a position which is lying vacant, the charge particle will tend to give up that extra energy and be trapped here will occupy this energy level and find an equilibrium position. So this is called trapping. And then sometimes there are potential wells. So there are positions which require a certain energy, and there are several such positions with the same energy level. They have to give up a small quantity of energy and can reach that potential well. But at the same time, so suppose there is a charge which is residing in a particular potential well, and in the vicinity there is a second potential well with the same energy level. So the charge will then tend to jump from one potential well to another potential well in search of an equilibrium position where these potential wells have almost the same energy. And this is called hopping of charge carriers. So trapping and hopping of charge carriers between localized charge sites may happen. Now, when you have a lot of free charge, all these involves free charges. So free charge is trapped in a particular physical space. The net result is there will be a polarization. So you have a lot of space charge here, and therefore you might have another quantity of space charge there, and there is a charge separation. So this kind of charge trapping and hopping of charge carriers can give rise to a certain slow process. So this is another polarization process, because you are creating localized charge sites which are separated by a finite distance. So therefore this contributes to this is like a process which is similar to polarization, except that it involves free charges. So this is another very slow process that we are concerned with. And this is a very slow process. Not only is it a slow process, it is also strongly temperature dependent, and these processes are found mostly in solids. You can imagine why it would be temperature dependent. When you apply temperature to the material, they acquire more energy. So these charge carriers that we are talking about, which tend to hop from one place to another, have more energy, and they are more willing to move around rather than occupy a particular position. Or if you already have trapped charges, they will tend to detrap and move to new sites. So these are the different kinds of slow processes which leads to polarization current flowing for a very long time. And sometimes this long time is at the level of days, several months. It can take for a polarization process to be complete. And generally, we are interested in these polarization processes. We see them in polymers, in polymeric insulation. So here I have an example of this kind of charge transport. These are certain particles. These are actually nanoparticles, or they could be microparticles. We'll talk about nanomaterials later. And this filler particle is embedded in a polymer. Now polymers have chains, and in a particular position of this polymer chain, there might be a segment where there are some charges, and there might be potential wells in the vicinity, and these charges can kind of hop from one potential well to another. So what you see is, this is called intra-cluster charge transfer. So charge is moving within a cluster. So these are kind of random locations, and these are kind of separated from each other. And what you see is, this is caused by the molecular structure of the polymer chain. So what you see is, there are certain charge particles which are moving around. They're hopping from one point to another, but this charge transfer is limited within this cluster. So it is an intra-cluster charge transfer, and we are not really bothered about it. However, if you apply more temperature, what can happen is, as you see here, some intra-cluster charge transfer continues, but at the same time, one of the charge particles may acquire enough energy to transfer from this cluster to the next cluster. However, it does not have enough energy to go from here to the other electrode. There is just sufficient energy from a charge to transfer from this cluster to the neighboring cluster. Similarly, another charge will transfer from this cluster to the neighboring cluster. This is called intercluster charge transfer. Now, what is happening here is, you don't really need the time required for a free charge to move from one electrode to the other. It is sufficient if you have movement of a charge carrier from this cluster to the next, and from the next cluster to the next, so that these are different charge particles which are moving between clusters. What is the effective uh, total effective situation here? Effectively, what is happening is one charge is transferring from here to the next, again another different one from next one to the next one, and so on and so forth. So if you think about it, there is an effective charge transfer from one electrode to another. It is not the single charge particle which is moving from one electrode to another. The electron or the charge particle has to move just between two neighboring clusters, but there is an effective charge transport from one electrode to the other, and this is called quasi-DC polarization. So DC polarization is, or DC charge transfer would be where you have actually one charge, one free charge moving from one electrode, traversing the entire distance to the other electrode. But here you do not have that actually happening, but in a much smaller time and at much smaller energies, so that you just need charge to travel from one cluster to another. You have an effective charge being transported from one electrode to the another, and therefore this is called quasi-DC polarization. As you can imagine, this is again a very slow process, and you need certain conditions to be satisfied for quasi-DC conduction polarization to quasi-DC polarization to happen. It's also called QDC. And then you have what is called segmental motion, where the polymer segment acquires enough energy to move around. Now, parts of the polymer segment will have positive charge and parts of it will have negative charge. So when there is enough energy for segmental motion, the segment moves around, and because the segment moves around, the charge centers move around. Again, you can imagine we are talking about very long polymer chains, and these are heavy, they move very slowly, so we are looking at very slow polarization processes. So this is to kind of give you an idea about what are the fast processes that we generally talk about in terms of polarization, and what are the slow processes that will need a very long time to complete in mostly in polymers. So if we look at the time scales of the different polarization processes, you have here in the 10 to the minus 15 seconds range, you have electronic polarization completed, which is where you have the charge separation between the electron nucleus and the between the atomic nucleus and the electronic cloud. Then in the range of 10 to the power minus 10 seconds, you have atomic polarization. After that, as I said, over the entire regime, from 10 to the power minus 10 to 10 to the power minus 5 seconds, you can have orientational or dipolar polarization. Then in the range of 10 to the power minus 5 seconds to 1 second, you have hopping polarization. 1 second to the order of 10 to the power 5 seconds. We are talking hours here. We are talking days here. We have space charge polarization, which we have already discussed. And within space charge polarization, you can cover all this hopping polarization and space charge polarization. These are all very slow processes. Now, if you want to measure the dielectric response, there are two different ways of doing it. One is the frequency domain dielectric spectroscopy, and the other is the time domain dielectric spectroscopy. Let me first talk about the frequency domain spectroscopy. As you can imagine, if these are time varying quantities, if I energize the dielectric material at different frequencies, I will see different polarization processes. If I apply a high frequency energy voltage, I'm no longer talking about DC energization. I'm talking about energizing the dielectric material with a very high frequency supply. In that case, only the fast processes will be able to be completed, and therefore the polarization that you measure will only be due to the instantaneous processes. Polarization is measured as permittivity. And as permittivity in the sense that it is the ratio between the capacitance of the material to the capacitance of a ideal electrode assembly with air inside instead of the material. So you will see that this epsilon, the permittivity that you measure at this frequency, will be very small. Now, as we increase the frequency, more and more polarization processes have time to complete. So at low frequencies, the permittivity of the material will increase rapidly. And therefore, the permittivity that you will measure will be much higher and very different from the permittivity that is measured at high frequency. So what I'm trying to say here is that the effect of the different polarization processes can be seen by energizing the dielectric material at different frequencies. And permittivity is a frequency dependent property, and the permittivity that you see at different frequencies will give you a measure of what kind of frequencies, what kind of polarization processes you are looking at. And frequency domain dielectric spectroscopy does exactly that. It measures the permittivity as a function of frequency. So permittivity is a complex quantity. It has a real component and it has an imaginary component, which we have already discussed. The real component is due to the energy storage capacity of the material, and the imaginary component is due to the losses in the material. And therefore, if you can measure these two complex quantities as a function of frequency, you should be able to get a measure of the different polarization processes. So therefore, epsilon star omega is equal to epsilon dashed as a function of omega minus j epsilon double dashed as a function of omega. So in frequency domain spectroscopy, we can think about an experimental setup where you have a specimen, you have a ring electrode, and which is the guard electrode, and you have a upper electrode and a lower electrode. The guard electrode is required to prevent the surface currents from flowing, and this is connected to a dielectric spectroscopy and a dielectric spectroscope, and you measure the capacitance of this material, compare it with the capacitance of an equivalent electrode geometry, and you give the permittivity. The permittivity is obtained as a measure of frequency. This is called dielectric spectroscopy. So this is the electrode assembly. Generally, the electrode assembly will be housed in an electrode cell. So this is the picture of a commercial dielectric spectroscope, which we have in the IIT Kanpur high voltage laboratory. We use it for our research purposes. So what you have here is the electrode assembly goes right in here. The electrode cell goes right in here, and these are the leads coming out of the electrodes. The entire cell is maintained at a particular temperature. We can also go to higher temperatures. Some equipment also can go to lower temperatures, like up to cryogenic temperatures, because as we know, polarization mechanisms are dependent on temperature, and they are also dependent on humidity conditions. So sometimes we can also control the humidity. So the sample will be held at a fixed humidity ambient conditions, at a fixed relative humidity conditions, at a fixed temperature, and the complex permittivity will be measured. So this leads to an automated system. As you can see in the computer, we have measurements of the real part and the imaginary part of the permittivity of a particular sample which is inside the electrode assembly. Now, I do not want to discuss the nitty-gritties of dielectric spectroscopy, but just to give you an idea about how dielectric spectroscopy can be useful in estimating the condition or the composition of an insulating material, I will just go through a few random examples. Now, in dielectric spectroscopy, what we try to do is we try to look at the trend that the complex permittivity follows over a wide frequency range. So how does the permittivity change with frequency, and how does it change with temperature? If the temperature changes, polarization mechanisms will change, and this will reflect in a change in permittivity. The other thing that I have already mentioned is that if you have low frequency polarization mechanisms, then as you measure the permittivity over frequency, as you go from high frequency to low frequency, you will see a considerable change in permittivity. So for example, here I have this is taken from published literature. This shows the real part of a complex capacitance of a Presburg sample. So I'm not looking at the complex quantity here. I'm only looking at the real part, that is a dielectric constant of various Presburg samples. So I have here 1, 2, 3, 4 different Presburg samples, and their constituents are different. As you can see, here The permittivity, of course, changes. At high frequency, one has a higher permittivity, but the variation with frequency is more or less similar for all four samples till you come to very low frequencies regions. In this region, this number 1 and number 2, they remain flat, and the permittivity does not change too much with frequency. However, number 3, number 4, what we find is that at low frequencies, the permittivity shoots up. As you can see, it shoots up from 250 to 350, and this goes even beyond 400. So that means whatever we have, so these materials are basically the same material with some additional, so some additives. And the quantity of the additive is varying from one sample to another. And the effect is that in number 3 and number 4, certain polarization mechanisms are set up which causes the permittivity to shoot up considerably. And the permittivity only changes if the permittivity changes throughout. So you have an increase in, so whatever filler has been added, whatever additive has been added causes the permittivity or the dielectric constant to increase throughout. But more than that, more importantly, what we can see is that the low frequency permittivity has increased largely. So whatever addition has been there is instrumental in setting up low frequency polarization mechanisms which are absent in samples 1 and 2. So right here, the trend of the complex permittivity or the real permittivity here over frequency gives us an idea about the constituents of the sample. Now this is at 20 degrees centigrade. If you measure at a higher frequency, a higher temperature, you will probably see increased permittivities. The shape may or may not change. The shape will only change if polarization mechanisms which are not possible at 20 degrees centigrade begin to happen at higher temperatures, which might happen simply because of the more energy that you're putting into the system. Here I have some examples of aged samples. There are various kinds of aged samples. These are humidity aged, these are thermal aged, and these are UV aged. These are the virgin samples, unaged samples of 3 unknown materials A, B, and C. And we are measuring the tan delta. So we look at complex permittivity, we look at the imaginary component. The ratio of the imaginary component to the real component gives us tan delta, and tan delta is plotted in these figures. So for this ABC, you can see that they behave differently. Their behavior with frequency is different. The tan delta is different for the 3 materials, and you see that there are some small peaks in the tan delta at certain frequencies. So that means the loss mechanism is higher at these frequencies, and that must be indicative of certain specific polarization mechanism. For example, here maybe we are looking at dipolar polarization, but here we are probably looking at some other low frequency process which could be QDC or something. Just by looking at the tan delta, it's not easy. I mean, it's not possible to make a judgment. There are many, we have to analyze a large amount of data and in various ways to be able to come to the conclusion that this is the polarization mechanism that is dominant. We do that in research, but I'm not going to go into this here. Now look at what happens to these tan delta curves when you age the samples and do the same measurements. In this case, what we have done in figure 3, we have aged the samples in humidity, which means we have exposed the materials to a very high humidity conditions for a prolonged period of time. So probably there has been water ingress, and the water ingress would not be the same in all cases. So as you can see here, this material A shows a high tan delta at these frequencies compared to the material A. So if you are probably thinking of using this particular material in conditions of high humidity, it might not be a very good idea to choose material BA. It might be a better idea to choose material C, which is less affected by humidity. Of course, from here you can also figure out how much degradation has taken place, what chemical changes have humidity caused in the material. I will not go into the details of how to figure that out. That is a long procedure, but it can be done. Similarly, in this case, you have the tan delta curves have changed because of thermal aging. Thermal aging means you have exposed the material to very high temperatures for a prolonged period of time. So ABC has been kept at a fixed temperature for a fixed time, and they have been affected differently. If you look at this curve C, you can see here, remember, C was not affected by humidity, but C seems to be very much affected by temperature. The tan delta shoots up considerably. The tan delta shoots up everywhere, and especially at low frequencies, it shoots up considerably. Whereas in this respect, A gives you a better behavior. So therefore, your choice of materials, just by looking at these graphs, and even if you don't go into figuring out what are the polarization mechanisms, roughly speaking, it is possible to conclude that it might be a better idea to use material C, material A when you expect high temperatures, and material C when you expect high humidity environments. Again, here you have a different kind of aging. This is ultraviolet aging, where the sample is exposed to ultraviolet rays for a very long period of time. And here too we see that the curves have been affected in a different manner. Tan delta has increased, but not a lot. And the changes that you see are mostly in the high frequency region. In these two cases, for thermal aging and for humidity aging, the changes that you see are in the low frequency region, or moderately low frequency region, always below 10 hertz. Whereas in this case, ultraviolet radiation seems to affect the polarization mechanisms which are operational at high frequencies. And it has been concluded that polar groups like carbonyl and hydroxyl deteriorate due to ultraviolet radiation. Of course, you cannot come to that conclusion simply by looking at it. Additional tests have been done. But the point is that dielectric spectroscopy measurements look at the variation of complex permittivity with frequency and with temperature, and this gives us an idea about what kind of degradation might have taken place, or what kind of chemical changes might have taken place in a material due to aging or due to manufacturing.